In the previous two videos, we looked at how to filter individual steps in a graph traversal using the Gremlin graph query language and Syndea's query builder. In this video, we will provide an example of stringing together such steps to complete an extended graph traversal. While this demonstration queries for a very specific pattern, hopefully it will be a useful guide in formulating your own queries. We start by defining our objective in words. Show all paths related to Syndea project DZ-SB01, filtered by isLatest equals true, where the starting vertex is of type TestRail case belonging to the repository TestRail at Intercax, the second vertex is of type activity, the third vertex is of type requirement, and the fourth vertex is of type requirement belonging to the repository JAMA at Intercax. In graph analysis, we think of this in terms of finding particular paths across the graph. We start at nodes of a specific type, TestRail case, then look for edges that connect them to a second type of artifact, activity. If that path exists, we look for a second edge connecting the activity to a requirement, and finally, a fourth artifact, also a requirement that belongs to a specific JAMA repository. We also require that the first and third edges belong to the Syndea project DZ-SB01. There may be multiple systems being modeled in Syndea Cloud. We want to exclude all the projects but one. The resulting query might look like this. We will break it down step by step. We start with the first vertex, which must be an artifact. We only want vertices of type TestRail case belonging to the TestRail at Intercax repository, in case there are other TestRail repositories recognized by Syndea Cloud. The where formulation looks for starting vertices that show a pattern like this, but it doesn't follow that pattern as part of the graph traversal. There are alternative ways to specify this path in Gremlin. Out, for example, represents a double step, an outward edge pointing into a vertex. We could rewrite this as two single steps with the same outcome. From the starting vertices, we look for an inward-pointing edge that is owned by the Syndea project container DZ-SB01. Remember that Syndea projects only contain relations between elements in different repositories, such as TestRail and SysML in this example. These relations can be of many types, but here we have not put a further restriction on the relation type. We have also restricted relations to only the latest versions, remembering that Syndea Cloud saves older versions of the relations as well. The opposite end of this relation must originate from a vertex of type activity. Here we have made an assumption that there is only one artifact type with the name activity. If there were more, this would create an ambiguity. We could use the type property instead, art type 6, which is a SysML activity, instead of the name property to eliminate this ambiguity. So far, we have only traveled to the second vertex. The next step in the query asks for outward edges leading into artifacts of any type with the name requirement. The earlier comment about type names is particularly relevant, since SysML, DoorsNG, JAMA, and perhaps other tools all have elements named requirement. We could use the type property of this vertex, or specify the owning repository if we need more precision. And we could also filter by the type of edge in this line. The final edge is also required to be in Syndea project DZ-SB01. Remember that the same SysML model artifacts might be used in several Syndea projects, representing different systems or versions of systems. To prevent results from different projects mixing together in the results, we should probably place this condition on all Syndea-managed intermodel connections. The final line specifies the last vertex. This is also a requirement, but specifically a requirement from the JAMA at Intercax repository. As with the first vertex, we use the where command to filter the vertices without actually traversing those edges. This becomes important because we have added the path command at the very end. This shows us the full path of the traversal. Without it, only the final vertex, the JAMA requirement APU, would appear in the result. In our result, there are only one set of elements matching the query pattern. This will not necessarily be true. There may be multiple sets of elements that match the pattern. We could further limit the result by specifying the individual name of any of the artifact vertices. Or we could replace path at the end with count, which would have returned only the number of pattern matches. These Zendaya training videos are not intended to be a substitute for learning the Gremlin query language. Gremlin has capabilities far beyond those illustrated here. You might start by exploring the links shown here to unlock the full power of graph analysis for model-based systems engineering.